Thank you. So today I want to talk about the earliest history of galaxy formation in our universe, and in particular this thing called Cosmic Reionization, whose importance I will try to convince you of. I'm going to start off with some context, and then I'll move into kind of a summary of what we think we know about these early generations of structure in our universe from both an observational and theoretical perspective. And I'll finish with some hope for the future as to what we want to do soon. All right, so this is a timeline of the history of the universe with the Big Bang at the left over here and the present day at the right. So that's a span of 13.7 billion years or so. The times are labeled on the bottom axis here. Okay, so this is logarithmic in time, or roughly logarithmic. So 13 billion years ago is this line right here. The upper panel is labeled with redshift. Okay, as light moves through the expanding universe, its wavelength gets stretched out or redshifted. And so astronomers often use redshift as a proxy for time. And I will show some plots with that, but I will try to translate back to time for you. Okay, so one of the key goals of cosmology is to tell the story of how our universe went from its very simple state shortly after the Big Bang to all the complexities we see today. Okay, and that's the aspect of cosmology that interests me most. The end point of that story is, of course, what we know best. We know that stars today are organized into galaxies. There are two main types of galaxies. Each has very well-defined properties. On average, galaxies are large today with 100 billion stars. The other era that we know quite well is back here, 400,000 years after the Big Bang, when the cosmic microwave background was last scattered. There have been dozens of experiments that have aimed at measuring that, most recently the Planck telescope. And so we have exquisite information about what the universe was like at this point. Right? And for those of us who study galaxy formation, the answer is it's a very boring universe because there's no galaxies there yet, of course. In fact, the universe is uniform to about 1 part in 100,000. People who study the CMB are fond of referring to it as a baby picture of the universe, which in one sense is, of course, correct, looking at the very earliest phases of the universe that we can image. But for those of us who study the galaxies in the universe, they aren't around yet. So it's better to think of these as kind of the DNA of the galaxies that are going to form, or the initial conditions out of which structure has to form. Over the last 20 years, there's been a lot of effort to push our understanding of galaxies backward in time. And as I'll tell you today, the most distant galaxies that we have observed so far are back here several hundred million years after the Big Bang. Okay, but the most distant ones that we have been able to study in detail stretch back to about 1 billion years after the Big Bang. And these galaxies are different than their local cousins or local descendants. They're smaller. They're growing more rapidly, and they're interacting with their neighbors more violently, right? But they are made of similar things, the same kinds of stars, the same kinds of gas clouds. We can understand them with the same physical arguments. So I think of these as kind of adolescent galaxies. Their major components are the same as the mature ones, but they're still growing up. What we haven't yet seen is what galaxies are like back here, okay? And that includes the moment when the very first galaxy in the universe was formed, whatever it looked like, right? Which was a very important change in the history of the universe, because at that point, the universe goes from being very simple, right? Basically, you can describe it with numbers like the matter density, the Hubble constant, et cetera, plus linear perturbation theory. But once the first star forms, okay, now all of a sudden you have radiation, you have explosions, you have complicated chemistry going on. And so it's a moment of transformation, okay, where the universe finally gets complex. That true infancy of the first galaxies and growing up into the structures that we can understand in this adolescent phase, all right, is the era of galaxy formation that interests me most, and one that we are kind of poised to understand in the next few years. So what I want to talk about today. This era has a number of different cutesy names. The one that is most popular right now is called the Cosmic Dawn, because this is the era when the first light sources filled the universe. All right. Now, I'm not going to talk much about the very, very first galaxies today, because we're not able to observe them yet, and we don't have much information on them. I'm going to kind of focus on the later, but still very young galaxies in here. And their landmark event is what is called Cosmic Reionization. And this is an animation showing how we think that event might have unfolded. The basic idea is as structure forms, you get hot stars inside these first galaxies, and those stars produce ionizing photons. Some of those photons leak out into the universe around them and make little ionized bubbles, which are these little blue blobs. Okay? As you get more galaxies and bigger galaxies, those bubbles grow and merge and eventually fill the universe. And once it is highly ionized, then we call this reionization. Okay? And this is important to astronomers for a number of reasons. Right? The first is that it is a global phase transition. Okay? It is one of just 3 points in the history of the universe where all the baryons did the same thing at roughly the same time. There was nucleosynthesis, there was recombination when the CMB was last scattered, and then there's reionization. Right? We know after this, the universe remains highly ionized to the present day. Okay? So it's just sort of a fundamentally important part of our universe's history. Another reason that the global phase transition is interesting is because at this time, about 95% of the matter in the universe was outside of galaxies. Okay? Although these galaxies have the most interesting objects in them, they contain a very small fraction of the matter. And so if you want to understand the overall evolution of the matter in the universe, you want to look outside of those galaxies. Additionally, as you'll see, I'll explain a little bit later, because so much of the matter is outside of these galaxies at this time, it's in some ways easier to understand what's going on by looking at all the rest of the matter at once, rather than try to find those isolated tiny points. All right, another reason it's important for astronomers is that in addition to ionizing the gas, you're also going to heat it. So it takes 13.6 eV to knock the electron off of hydrogen, but usually the photon that you have has 15 or 20 eV. And those few extra electron volts per hydrogen atom correspond to a heating of 20 or 30,000 Kelvin. Now, we don't know what the temperature was before this reionization event, but it was probably at most in the hundreds of Kelvin. So this is heating by 2 orders of magnitude. And along with the heating, you increase the pressure of the IgM. Right? And that affects the way in which all of this material that's currently outside of galaxies, all right, will fall onto future generations of galaxies. Okay? And one example of that is in our own Milky Way. Okay? We know that the vast majority of stars in our Milky Way formed long after this era was done. But there are some stars that were formed very early on. And in particular, there are a number of tiny, what we call dwarf galaxies orbiting the Milky Way, several dozen of them. And nearly all of them have very, very old stellar populations that have not been able to form stars in the last somewhere between 10 and 12 billion years. And one possible explanation of that is that these tiny clumps, okay, were able to form stars, and then the universe got reionized. Okay, and as you ionized the gas, you heated it above the escape velocity, or you heated it and so increased its velocity above the escape velocity of those dark matter clumps. Okay, and that gas was all able to just flow away, and you choked off the fuel supply of these galaxies. Okay, so essentially, reionization is setting the stage for future generations of galaxies. Right. Unfortunately, we know very little of this about this era so far. So I mentioned that we know the universe has been highly ionized for a long time. We know that is true back to a redshift of about 6, which is about 1 billion years after the Big Bang. Okay, so reionization must end by that point. The second thing we know comes from the cosmic microwave background. So when the CMB was formed, the IgM became neutral. And as long as our CMB photons are traveling through neutral material, they don't interact. But once the universe is reionized, we have free electrons around, and those photons can Thomson scatter off of them. Right, so that smears out the intrinsic CMB fluctuations. But because it is directional scattering, it also generates polarization. And so a number of CMB experiments have tried to measure this polarization. Most recently, the Planck collaboration, okay, measured the optical depth of this process, which is about 6.5%. Okay, if we convert that into a reionization history, so suppose the universe remained neutral until some moment when it was instantaneously ionized and remained ionized for the rest of time, right, that would say that reionization occurred sometime at redshifts of 7 to 11. So that's 450 million to 850 million years after the Big Bang. Okay, and these two things are consistent. We know we're done by this, which is 1 billion years after the Big Bang. And so it's going on not too far before that, we think. All right, so that's what we know directly about reionization. But there are other ways to study these early galaxies, and that's the more traditional astronomical observation of just going out and doing a survey to find those galaxies. So I want to mention a couple such surveys. The basic challenge is that these things are very, very distant from us, okay? And because they're so distant and the light has traveled so far, it's redshifted. And so to look at these things, you have to look in the near infrared. So one effort to do that came out of what's called the ultradeep field. So the ultradeep field is a tiny patch of sky that the Hubble telescope started to look at more than a decade ago with very, very deep observations. So very, very long, staring at this little patch of sky for a very long time. Over those 15 years or so that these observations have been done, there are now thousands of hours that have been put into looking at this one patch of sky. The most recent effort is called the UDF-12 because it happened in 2012, right? And I was part of this team, and what we did was we looked at the field with a new camera on the Hubble telescope called the Wide Field Camera 3 for about 4 days, looking at in this near infrared filters to try to observe light from, and identify these earliest galaxies. Okay, we were trying to answer two questions. I should say this is the field. There are little squares here which show you where these distant galaxies are. You can't see them because they're incredibly faint. But we were able to find several dozen at the times relevant to what I'm saying here. Okay, so the questions we wanted to ask is how many galaxies are out there? Because those are the sources that we think are doing the ionization. And second, what sort of stars live inside of them, which is a much harder question. But ultimately, you need to answer that to know how efficiently these galaxies can create ionizing photons. So that was in 2012. Since then, there have been continuing efforts. As I mentioned, there are thousands of hours in the ultra-deep field. And so the prospect of increasing that by a square root of 2 would require a whole lot more telescope time, and we're not up for that. So instead, people are using gravitational lensing to try to look at these eras. So the idea is Hubble is staring at 12 massive galaxy clusters. This is one of them. Basically, the orange blobs that you're seeing here are in the galaxy cluster. The blue stuff are objects behind the cluster that are magnified by it. And so you can use these gravitational telescopes to go to look at very, very faint objects below the limit of what you can find with the ultra-deep field, although only over the very, very small patches of the sky that are strongly lensed. So this is ongoing, but some results have already come out. All right, so the basic product of these kinds of surveys is what we call a luminosity function. So you can't read the units here, but astronomy units make no sense anyway, so that doesn't really matter. What's down here is a proxy for the luminosity, and it's backwards. So these are the very luminous galaxies, and these are the faint ones. And then the y-axis is the number density of those galaxies. Okay, so there are very few bright galaxies and lots of faint ones. These are redshifts of 7 and 8. That's 850 million years after the Big Bang and 600 million years after the Big Bang. Okay, and you can see that the bright ones are rare, so there are big error bars there. But we have pretty good measurements on how many of these galaxies there are at these times. The challenge, though, is it turns out that there are way more faint galaxies than bright ones. And there's no reason to believe that the number of galaxies cuts off at exactly where our telescope stops being sensitive, which is the limits that are shown here. Okay? So there are likely a lot of faint galaxies out there that we can't see. And in fact, if we want to reionize the universe by a billion years after the Big Bang when we need to, then most of the light actually has to be coming from unobserved populations. So one thing you can do with the frontier fields is look for fainter galaxies with lensing, and that's been done. It pushes this so far, about to here. Okay, and the important point is that the shape doesn't change here. Okay, you can just extrapolate. With the UDF-12 and subsequent programs, including the frontier fields, we've also found more distant galaxies at earlier times, but there are only a couple dozen of those, and so you can't get strong constraints from them. Now, to get a reionization history from these galaxy observations, we need to make a number of assumptions. One of them is how many of these very faint galaxies there are. Another of them is how do we go to earlier times to look at what the galaxy population was like then. Right? And to do those, one can extrapolate. Okay, I prefer extrapolation with some physical understanding of at least how you're doing the extrapolation. So a UCLA undergrad, former undergrad, and I have been trying to do some simple models to try to understand these galaxies. Okay, and I'm not going to get into the details of the model, but basically what it's trying to get at is down here is the mass of the dark matter clump in which the galaxy lives. Okay, and up here is the efficiency with which that clump can turn gas into stars. All right, and so when you try to do this model, you end up with a shape that's like this. It has a peak, okay, and it declines towards small galaxies and possibly to large galaxies. Now, this shape is exactly the kind of shape you get for galaxies at low redshifts, at late times, that we understand very well. Okay, there are sort of some differences, but qualitatively, this is what we kind of expect this to look like. Once you have this, okay, then you don't know, from the data here, you don't know what's going on in the very, very faint or low mass galaxies, but you at least have a framework for understanding, okay, how to extrapolate in that direction. And I have three different cases here. One's very optimistic, one's very pessimistic, and one is kind of like what happens at later times. And armed with this, we can then, since we know how structure forms in the universe, or think we know, you can extrapolate this also to the earlier times, right? And you can generate a total star formation history in the universe. So here, this x-axis is cosmic time, going from early times at the right to late times over here. And this is the density of star formation going on in the universe as a function of time. Right, so this is a complicated plot. Okay, I just want to point out a few things. At late times, you can see a few data points. Those are real data, right, with real error bars, and they're pretty small, right? Those are the measurements I just showed you. At earlier times, we have these galaxies, but there are very few of them, so the measurements become much more uncertain. Right, so what we've done is we've calibrated our models to the good measurements, and then we can extrapolate with these three solid lines, depending on what you assume about those faint galaxies. Okay, and so the star formation rate is going down, okay, at some unknown rate with large uncertainties depending on what you think happens with these faint galaxies. Right, once we have this extrapolation to faint galaxies into early times, we can use this to build an ionization history, or guess an ionization history. So again, this is time going from early times at the right to late times at the left. The y-axis now is neutral fraction. So at early times, the universe is mostly neutral. At late times, it becomes ionized. This white curve with the red band around it is what you get with the kind of extrapolation I just described. Okay? And it turns out, well, so you have to assume three things, as I said. How many faint galaxies are there? What happened at earlier times? And then one more thing, which is how many ionizing photons get out of your galaxy. And this turns out to be a crucial step. We can look at galaxies nearby, and we can try to measure how many of these ionizing photons get out, and so would be able to reionize the universe. And the answer is almost none, a few percent at best. Okay, so we have to assume something about this. And in order to make reionization finish by the time we think it must, which is basically this vertical line here, right, I have to assume somewhat higher, a 20% escape fraction, all right, which is not ridiculous, but a little bit of tension there. Right. The other thing we know, as I said, or think we know, is the optical depth to the CMB. Right? And if you just do what I've described, this extrapolation procedure, make sure it ends at the right time, it turns out you're in the ballpark of that CMB measurement that I mentioned. You're on the low side, but you're on the ballpark, in the ballpark. And so things, okay, which come from astrophysical constraints on the neutral fraction. Those are interesting. I've worked a lot on those, but they're all model dependent. So I don't want to get into the details of them, especially because they are not very interesting constraints at this point. Okay. The bottom line right now is that we can, based on these galaxy observations, we can construct a sort of fiducial model for how reionization happened that's consistent with those two numbers that we know. All right. But of course, we want to know better, want to do better. And so to describe how we're going to do better and why this is an important question to ask, I want to talk about how we theoretically model reionization. Right, so the goal is basically assume that we know what the sources are doing, what these galaxies look like. How do we go from those sources to some map of the ionized bubbles and whatnot during reionization? Okay. if you had isolated galaxies, this would be a very easy problem. I have some galaxy. If I know how many ionizing photons it produces, I could just draw a sphere around it such that there's one hydrogen atom inside that sphere for every ionizing photon that I started with, and I'd be done. The challenging thing turns out to be that these galaxies at early times are highly clustered, close to each other, whereas these ionized bubbles are very large. And so you typically overlap another galaxy, and so now you have its photons to add to your pool, and so that you don't need two photons for the atoms in this overlap region, so you make your region bigger, and you overlap more galaxies, and on and on. Right? So fundamentally, it's a counting problem, okay, but we need to count in the proper way. And the right way turns out to be to reverse it, and instead of starting at one galaxy and working outwards, to start at a whole bunch of galaxies, a large volume, and work inwards. So you pick some big region of the universe, you ask whether there are enough ionizing photons produced inside to ionize it. The answer is yes, then you've reionized the universe, so you're done. The answer is no, then you zoom in, and you keep zooming in until either the answer is yes, or you've run out of galaxies, okay? So this procedure sounds very, very kind of brainless, okay, but it turns out to be very effective at describing reionization. So this animation that I showed you earlier was actually not a complicated calculation following individual photons or anything. Instead, it was just this counting argument implemented in some made-up volume of the universe, okay? And if you compare these kinds of calculations, which we call semi-numerical simulations, to the full thing with radiative transfer, with hydrodynamics, with all the bells and whistles that we can put in right now, these models do quite well. They get kind of 90% of the right answer in a small fraction of the computing effort. All right, one can also use this argument to make analytic predictions of how reionization works. And this is significant because if we want to actually understand the kind of physics behind it, we want to be able to express that in some clean fashion. So pretty much the first thing we did with this model was to predict how big your ionized bubbles would get throughout reionization. So down here is the radius of the bubble in megaparsecs, and this is the fraction of the ionized volume that's in bubbles of a given size, with the different curves corresponding to different points during reionization, okay? So the key takeaway when we did this calculation was that these ionized regions get very large. Right? So tens of megaparsecs across by the middle of reionization, which means that there are actually hundreds of thousands of galaxies inside each of these bubbles, which is why that overlap problem was so significant. The other nice thing about this was that in general, right, bigger things are easier to see than small things, and so this meant that we had a better shot at being able to study these structures. However, it turns out if you look in detail, right, this analytic prediction with our the physics that we understand does not match the sizes that you actually get in the semi-numeric simulations. Okay, so this is the same kind of plot. Radius down here, fraction of the volume in bubbles of given radii here. The three black curves are the analytic prediction that I just showed, and the red and the blue curves are different ways of measuring the sizes inside these semi-numeric simulations. All right, so the bottom line is our model was about a factor of 3 wrong in radius, which means more than an order of magnitude in volume. Okay. So why is this happening? All right, well, it has to do with the complexities of any phase transition like this. Okay. In particular, you can understand it with percolation theory. So percolation theory is the study of how random processes fill spaces, essentially. And this is a simple example. It's a 2D grid. Okay, you can think of it as starting off white, and then you drop down, you fill cells on your grid with some probability. And the 3 panels show a relatively small probability, medium, and large probability. And so percolation theory is studying basically the structure of the pieces that emerge when you do this filling process. Okay? And of course, that's an obvious analog to reionization. So probably some of you in the room know more about this than I do, because it's used quite a bit in condensed matter physics to understand disordered systems and impurities and such. It's also studied by mathematicians because it's the simplest example of a phase transition out there. All right, so one of the generic features that you get in percolating systems is the formation of what's called a percolating cluster. Right? So there is some threshold as you fill this space with the black dots right, at which you are able to go from one side of the system or simulation to the other while traveling only through the black dots, okay? That is the percolating cluster. So if you had an infinite system that you could simulate, it turns out that this region is actually infinite in size, and that it is unique, okay, and that it always appears in the infinite limit, at least, at the same filling fraction of your system, okay? So we can look in our reionization simulations and see that the same thing happens, okay? So this is ionized fraction down here, and this is the probability that an ionized pixel is in the largest ionized region in the box, okay? The curves that go up like this are all different realizations, just sort of different boxes with different initial conditions for a box. And you can see they all basically behave the same. Okay, somewhere around 10% of the way through reionization, we all of a sudden get a large fraction of our ionized volume in this largest ionized region. Okay, and over time it grows to encompass almost all of the ionized regions. Okay, ionized volume. Now there's a difference from sort of standard percolation, okay, which is shown by the green curve, or two differences that I'll mention. One is that this infinite percolating cluster appears much earlier in the process for reionization than it does here. And that's because reionization is not a purely random process. It's driven by the underlying density field, which has large-scale correlations. Okay? And then for the same reason, if you look at the shape of this green curve, it starts later, but it actually ends, so it consumes all of the ionized, it would consume all of the ionized regions quicker, steeper. Whereas in the real universe, there's this long tail. Okay? So the bulk of the ionized volume is inside this region very quickly, but it takes a long time to get everything inside of it. Right? And that's from correlations as well. Another generic feature of percolation is that you get scale-free behavior at the percolation transition. Okay, so this is a similar plot to the one I showed you before. Down here is the volume of our ionized regions, and this is the fraction of the volume in each size. Okay? The red curves here are what this distribution looks like at the percolation transition, right when this cluster appears. Okay? The thin and the thick are just above and just below the transition. The blue dotted curve that you kind of see poking out down here, I hope, is just a power law. Okay? So this is described very closely by a power law. The other curves are this distribution at different times during reionization. So the farther away you are from the percolation transition, the smaller your ionized bubbles get. There's some, basically it follows the power law and then cuts off. Okay, so we see that this scale-free behavior happens during reionization, although the details are different than one might expect because of the correlations again. But you may be wondering, if I have this scale-free distribution, what does that mean relative to the measurements I showed you before of the sizes of these ionized bubbles, okay, taken from the numerical simulations that show not a scale-free distribution, but that there is this well-defined peak size. Okay, so what's going on? The difference here is that I'm defining an ionized bubble differently. Right? In percolation theory, what is typical is to basically take fully connected regions as fully discrete regions. So if I have a big spherical blob over here and a big spherical blob over here, and some narrow serpentine thing connecting them, I would count that as one single ionized region. Okay. But intuitively, if we looked at a map, that's probably not what we would do. So the measurements over here are meant to do it more intuitively. So then I would have one ionized bubble over here, one here, and then a third one joining them. Okay. So what this is telling us is that the structures that we're seeing, although they may be scale-free, okay, their components appear to have scales in them. But we don't understand entirely where those scales come from. My guess is that it has to do with the percolation, the stochasticity of percolation itself. Okay, but we haven't sorted that entirely out yet. Here are some examples of the kinds of structures I'm talking about. So this is another just simulation of reionization. The red and the blue are both ionized here. The blue is the largest ionized blob in the simulation, and the red are other ones that are separate from it. So this is just after the percolation threshold. A little bit later, again, the blue is the percolating cluster, and you can see its complex structure here. So you see a blobby thing here, and then a narrow channel connecting it to the rest of this, and that's typical. And later, by 25% or so of the way through reionization, that one blob has basically taken over the whole thing. All right. So we don't entirely understand this process yet, but we have a pretty good handle on the physics that are driving it. But things get a lot harder towards the end of this reionization process, right? And that's because by the end, it's not the sources of the ionizing photons that matter, it's the sinks, okay? The places where those photons are being absorbed. Right? So it turns out that the universe is not completely uniform, of course. There are dense blobs, or clumps, small clumps in there that remain, if not neutral, at least optically thick to ionizing photons, even after their surroundings are highly ionized. Okay? At late times in the universe's history, we can identify these individually. We can't do that during reionization, okay, but we expect that they are there. So how do these affect things? Well, if your ionized bubbles are small compared to the separation of these clumps, then the clumps don't really matter because very few of your photons hit them. But once your bubbles get large compared to the distance between these clumps, okay, they are going to, most of your photons are going to be wasted being absorbed by these clumps, okay? The problem is that in order to model how these clumps take over, we need to know their properties, and as I said, we can't observe them. Right, so instead, what we're trying to understand now is basically the universe just after reionization completes. Find how the clumps are behaving there, and then extrapolate backwards. Okay, so I'm going to just tell you about one example kind of observation we can do. All right, so the way you study the neutral content of the universe through most of its history is with what's called the Lyman alpha forest. You have some very bright light in your background, usually a quasar, and you take a spectrum of it and you see how much absorption it suffers. Okay? So that's highly variable, but if you average the amount of absorption over large chunks of the universe, in this case 70 megaparsecs, all right, then you can try to understand the variations. So this is redshift here again, okay? So reionization ends at about redshift of 6 out here. The y-axis here is the amount of neutral absorption you're getting measured in optical depth. Right? And each of these blue points is a 70 megaparsecs chunk of some spectrum, okay? So well after reionization at the left of the figure, there's not much absorption, and it's well behaved. There's not much scatter, okay? So the yellow point here is a simulation, and the red band around, or the orange band around it, is sort of the scatter you naturally expect. Okay? As you go farther back in time, though, you start to get this population of points that are much more optically thick or have much more neutral gas than we expect from these kinds of standard models. All right, so what is that coming from? Well, one possibility is these clumps that I just described. Okay, so this is another one of these simulations, in this case of the ionizing background. Okay, what the color scale is actually showing is how much absorption you're getting from the gas, from the neutral gas. A lot of absorption is black, not much is white. So the way, long after reionization is over, so down here, you can treat the radiation background as uniform, the ionizing photons as uniform. Right? If you do that, then what happens is you get variations in the absorption, right? The most transparent region here is going to be what we call a void in the galaxy distribution. That's a region without much matter in it, and so with very few galaxies. There's just not much matter there to do absorbing, so it's mostly transparent. Okay. However, right, that neglects the fact that the radiation background is actually quite inhomogeneous at these early times. So if you imagine I'm in one of these voids in the galaxies, there aren't many sources around. So my ionizing background is going to be small. Well, if my ionizing background is small, then I'm going to have more of these clumps sitting around because they can't be destroyed as efficiently by the photons. And if there are a lot of clumps around, then I actually can't even see as far as I thought, so I see fewer sources, so my ionizing background is even lower. Right? And so you get this feedback cycle, which ends up reversing the behavior. So once I add fluctuations from these absorbing clumps, okay, then this region that is a galaxy void, instead of being transparent in the typical picture, ends up being opaque, right, after you account for all of these clumps. So essentially, if this is correct, right, then mapping out the universe slightly after reionization allows us to learn about how these clumps are filling the universe. Right. Now, that's not the only story, though, because it turns out that there's another competing model by Anson D'Aloisio and company, right, that has another explanation for this scatter. And their explanation goes back to the heating that happens during reionization that I mentioned at the beginning. So if you imagine that you ionize a piece of the universe early on, it turns out it cools after that. And so it ends up cooler than a region that you've just ionized. And so you get scatter in the temperature field. And that temperature affects the recombination rate of the gas in your regions. And so it affects the neutral fraction. The interesting thing is that these two models make opposite predictions for the nature of these opaque regions. In this case, in our case, these opaque regions are voids. In their case, those opaque regions turn out to be clumps of galaxies. Right? So we can go and we can test that in the future. Right? This is an overlay of the opacity with the galaxies are shown in little red dots. Right? So here is an opaque region, and there are not many galaxies in it because it's a void. And here is an overdense region, okay, that would be transparent in our model, and there are lots of galaxies in it. So you can go do this test. It's a hard test to do because it's looking at the universe over 70 megaparsec chunks, which is a much bigger piece of the universe than we're used to looking at with galaxy surveys that go this deep. Right, so, but one possibility is a telescope called WFIRST, which will have a very wide field of view and be able to do this efficiently. All right, so I've told you what we know about galaxies during this early time. I've just told you that there's a lot more we can learn about the reionization process. So how are we going to go observe that process? Well, many of you here will know because Aaron Parsons is one of the leaders in building experiments to do this. But the goal is to use the hyperfine transition of neutral hydrogen, right, which the spin interaction of the electron and proton produce a photon with a rest wavelength of 21 centimeters. And the idea is essentially because there is so much neutral gas around during and before reionization, even though this is a very weak transition, we can go out and we can image the universe in this transition. The nice thing about that is because it's a spectral line, we can measure the entire history of the process. So imagine two 21 centimeter photons emitted at different times. Right? The one emitted later travels less through the universe, and so redshifts less, and so ends up at a smaller wavelength, okay, than the one that is more distant. And so by slicing an observed wavelength, we can slice in time, and in principle make this kind of movie. So this is the intensity of this 21 centimeter background as reionization progresses, and the black blobs here are the ionized bubbles growing. All right. This is also nice because it's the galaxy surveys measure the sources. This is looking directly at the intergalactic gas, and so together we can learn more than we can individually, and I'll mention that in a little bit. And finally, because it is such a weak transition, we can go all the way back to even before reionization and look at a large swath of the universe's history. So to sort of orient you into how this background works, I want to kind of step through a simple picture of it. This is what we call the global signal, and the idea is imagine having a telescope that observes some large chunk of sky and just takes a spectrum. So you're getting the average intensity of this background. So we're going to measure that intensity in what we call brightness temperature units. So this is millikelvin. I'll tell you why that amplitude is important in a little bit. We measure it relative to the CMB. So this horizontal line is no signal, okay? And then the y-axis is observed frequency. Cosmic time starts, goes from left to right. So early times here, late times over here. It turns out that before the first galaxies even form, there is a signal. It's very weak. It's very, very hard to observe. I don't expect to do this. But it's very easy to predict is the nice thing about it. And so you can use it as a probe of weird things like dark matter decay or primordial black hole evaporation or stuff like that. By the time the first stars form, which is about 50 million years after the Big Bang, the signal has almost vanished, though. Once those first stars form, then they turn the signal back on by flooding the universe with ultraviolet photons. So some of those photons are absorbed by the hydrogen-electron transitions, and during that, you mix the hyperfine states. It turns out the universe is cold at this time, and so you end up with an absorption signal. We don't know the amplitude of that signal, of course, because we don't know anything about these first stars. But these are some kind of representative models that hopefully you can sort of see. Now, of course, these first stars form in clumps. And so what really happens is they turn on and flood the universe, the regions nearby them first. And so you're going to get cold regions around those first galaxies, right? And those cold regions will eventually grow and and fill the whole universe. Shortly after the first stars form, the first black holes most likely form. And those black holes are important because as gas falls onto them, it gets heated to very high temperatures and produces X-rays. Those X-rays can then travel through the universe and heat the gas. And that's going to transform your absorption signal back into emission. Right? Now, again, the precise spectrum that you get will depend on what kind of sources you have. Right? But you can learn things like the characteristic mass of these galaxies or their local environments, or these black holes, sorry. So these are some models from my postdoc, Jordan Baraka. Here are early times over here, so the first stars turn on, and then he has a bunch of different models for the black hole heating, showing the kind of range it can take. And these are varying both the mass and the local absorption around these things. Again, the black holes form in particular parts of the universe. They heat the universe nearby first, and so you're going to get contrast between hot and cold if you can make maps of this process. And then finally, once you have enough galaxies around, reionization gets underway and destroys your signal. Okay? Now, I mentioned that this is complementary to the galaxy studies, and the reason is that most of the light is coming from the very faint galaxies that we can't see. And this is just an example of how you can discriminate with this. So here's a galaxy luminosity function. All right, here's the limit of our observations. And then the different curves are different acceptable fits to it, but doing different things with the faint galaxies. And those correspond to the 3 different solid curves in this panel. All right, so it makes a difference to this 21 centimeter signal because the faint galaxies are what are driving it. So there are hopes to observe this so-called global signal. I'm part of a project called the Dark Ages Radio Explorer. And the idea there is to fly a radio telescope to the far side of the moon and try to map out this spectrum from about the time the first stars form down to the time reionization is getting underway. Now, why are we doing this on the dark side of the moon? All right, well, there are 3 challenges to observing this signal, at least 3. The first is that it is 1.4 gigahertz redshifted by a factor of 10 or so. So we're in the 100 megahertz range, which is used by people quite a bit, right? FM radios and all that. A second reason is the ionosphere, which is refractive at the higher frequencies and becomes opaque at the lowest frequencies. So these are the motivations for DARE. We want to get above the ionosphere so we can study the very lowest frequencies. But it turns out it's not good to just orbit Earth, because then you see the radio contamination from all over Earth. So you go to the far side of the moon and use the moon to actually physically block the contamination from Earth. However, that still leaves you with the third challenge, which are the other astrophysical foregrounds. So I mentioned we measure our signal in millikelvin. It turns out that the radio background that we get from our own galaxy is 10,000 to 100,000 times brighter than that signal that we're seeking. So what we're really trying to do is make precise observations of these spectra and discriminate what's the cosmological signal from what's contamination from our own galaxy. All right. So this is another movie showing, so DARE and its instruments like it would measure this average background. But of course, we want to map those structures I mentioned. And this is a movie showing what those structures are going to look like. Sorry. So the left is showing a map, OK? This is before the first galaxies form, nothing interesting happens. But you're about to see the first galaxies turn the universe blue, which is cold. And now the black holes are forming and heating the universe. And then the black dots here are the ionized bubbles that are destroying your hydrogen. Okay? So we'd love to make maps like this. But because this foreground is so bright, it takes a huge instrument to actually be able to do that in detail. So instead, what we're focused on in the near future is the statistics of this map. Right? And at the right, I'm showing what's the power spectrum. So here's wave number down here, and the power spectrum is the y-axis. I'm not going to get into the details of that, except hopefully you're noticing that it's wiggling around a lot. And so by measuring those wiggles, we can pin down what's happening with these early sources. There are already several experiments that are making these measurements. Most important here is, of course, PAPER, the precision array to probe the epoch of reionization, which Aaron and his team work on. This is the power spectrum that they have measured so far. So the data points around here are their measurements. They're all really just upper limits. Okay. These other little triangle points are from other experiments. This predicted signal that we get from sort of a vanilla model of the reionization epoch is this purple curve. So it's about an order of magnitude away. All right. This cyan dashed curve is a plausible but probably crazy model. And that's sort of at the limit of what Aaron and his team are starting to rule out, which corresponds to very little X-ray heating, basically. The good news is that these constraints here are about what one would expect given the size of the telescope of paper. So that means that that's because the experimental teams have figured out how to separate these very bright foregrounds from the cosmological signal that they're looking for. So the trick now is to build a telescope that's sensitive enough to actually make measurements down here. And that is called the Hydrogen Epoch of Reionization Array, or Hera. And this is a photo. So this is an experiment that has already been funded by the NSF. We went to them recently for the full funding. These are 19 dishes in the South African desert. The beginnings of an array to make this measurement. And then this is an artist's conception of what the core of the array will look like when it is complete. This is 320 telescopes plus 30 that are out of the field of view. So this is going to be a completely transformative measurement of the reionization era. So this is a plot similar to what I've shown you before. Redshift down here, neutral fraction up here. So going from high neutral fraction to low. These are the astrophysical constraints that I wasn't going to tell you about. The gray band is what is allowed currently. And the pink band is what Hera will be able to, the constraints Hera will make after a season of observation at full capacity. So by the end of the decade, if it's built according to schedule. So that would be an amazing improvement on understanding this early reionization era. And so we're all very excited and keeping our fingers crossed that we get the funding. So I will end on that optimistic note. I hope I've convinced you that this is a very interesting era to study, and we have some great prospects for making progress in the near future, both in understanding reionization and using that to sort of leverage our understanding of the sources driving it. Thanks.
Early in the talk, you mentioned measuring, how do I put this, future, tiny little galaxies embedded in dark matter. So you're able to take measurements of dark matter now?
No, sorry. The galaxies, in our picture, the dark matter collapses and forms a gravitational potential well into which the gas will eventually fall. So we think every galaxy is surrounded by dark matter. We're not directly measuring the properties of that dark matter. Although there are ways of, so because the dark matter density field is driving everything, for example, the way in which galaxies cluster together is ultimately driven by the dark matter field. And so if you measure the clustering, you're learning something about how the dark matter structure is forming too, but you're not learning about the properties of the dark matter directly.
So what does the stars cool?
Okay, so what's important is that the gas is colder than the cosmic microwave background. So the CMB is a relativistic gas in an expanding universe, so its temperature goes like the volume to the 4/3, right? Whereas the baryonic gas is a non-relativistic gas in an expanding universe, and its temperature goes like volume to the 5/3. So as the universe gets bigger, the gas cools faster than the CMB, unless there's some energy exchange between them. For a while, you can do that for a while after the CMB is last scattered, you do that with Compton scattering. But when the universe gets to be big enough and cold enough, that becomes inefficient. All right, big enough, cold enough, and neutral enough, it becomes inefficient. So the gas ends up being very cold. The stars flood the universe with these UV photons, which scatter around. And because the gas is so optically thick, they bring the essentially temperature of this, the excitation temperature of this transition into equilibrium with the kinetic temperature of the gas, which, as I said, is cold.
The percolation theory understanding of how these ionized regions are is that going to lead to suboperational
So both. I think one way, as everything I've told you in this talk has been sort of couched in our picture, this photon counting picture of how reionization works. And if we want to kind of break out of that picture and do kind of more fundamental tests of what, just throw aside what we think we know about how galaxies form and just have some generic set of ways you might reionize the universe, percolation theory is an efficient way of sort of spanning that space, I guess is the way to think about it. The idea, so at the level of like the power spectrum measurements that we're all thinking about right now, the connectedness of these ionized bubbles doesn't matter a lot because the power spectrum, I mean, in some ways it's the simplest statistic you can do, right? And it's throwing out a lot of the interesting information about where the bubbles live relative to the galaxies and that kind of stuff. So I don't think that it manifests strongly in that power spectrum. But if you go to the next phase of trying to make the maps, right, then you're going to be trying to look at the structures in detail compared to the sources inside of them. And then I think you really need to understand in some detail how these ionized bubbles are able to grow. It's not obvious that you will, for example, be able to see the percolating cluster because, as I said, it's built of these blobs and narrow channels, and those narrow channels are going to be harder to observe. But I think it's going to have some effect on our how to use images to actually get physics out.
I have a related question. These percolating clusters, does it depend on the pixel scale?
No. Well, yes. Are you asking in the context of like our reionization simulations? Yeah, okay. Not strongly. So you can, so everything I've done, the experiments I've done are all in this sort of semi-numeric limit where we're not doing real radiative transfer and all those things. So on some level it must matter. But if you vary the box size by a factor of 4, well, 4 in radius, or the pixel scale by a factor of 4 in radius, it all looks roughly the same. There's not a big change. This percolating cluster has been seen in simulations. It's seen at like a 12% ionized fraction instead of 9% that we're seeing. So that's, I think, this sort of systematic uncertainty.